Greetings and welcome, internet friends. Mr. Waddy here today, and I've got a multi-day lesson on a whole bunch of properties of radicals and rational exponents. But before we get there, I've got this exploration one for us to consider, looking back at our old properties of exponents. And by the way, these can be found in the Algebra 1 textbook, Chapter 6, Section 1, if you're looking for them. And yes, I do have some Waddy Math videos that you can go check those out if you want to go on a little jaunt down memory lane. And so here we go. Let's see how well I can match these. Let's see, I'll get rid of my inkwell here. So a to the negative second power would equal 1 over a to the positive second power, assuming that a is not negative. That is the negative exponent property. Yes. Where, right, we summarized that by saying if someone has an unhappy negative exponent, you can move it downstairs and now their exponent is positive. Or vice versa, if someone was in the denominator with a negative exponent, then they would move upstairs and get a positive exponent. And yeah, we wouldn't even have to write that one down. All right, a, b, all to the fourth. So that's a product raised to the exponent of 4. And this is kind of like distribution. It turns out that actually we've got both b and e are similar. You can distribute exponents over multiplication as well as division. And so this would be a cubed over b cubed. So let's see if we can figure out the name of those things. Power of a product. I was taking the power of a product. A product is the outcome from multiplication. So power of a product. Oh, I should cross these out. That would be sweet. Power of a product, Charlie. And power of a quotient, golf, right here. Cap G. A to the third, all to the fourth is the property we had was where we multiply those exponents. I guess I'm showing the middle step there. So a power raised to another power, you multiply those exponents. Power of a power property, bravo. And a to the third times a to the fourth. If I multiply two things of the same base, that is when we add the exponents. And so we would have had a to the seventh. And so that was a product of powers. I was multiplying two separate powers. And so that was alpha. A to the sixth over a to the second. Dividing two things of the same base, you would have subtracted the exponents. And you'd subtract the bottom from the top. Although there are some other shortcut tricks if you're getting fancy for all those properties of exponent speedrunners on Twitch. Don't know about you, but you could learn some cool shortcuts later. So anyways, a to the 6 minus 2 is a to the fourth. And what was I doing? I was doing a quotient of powers. And so that's foxtrot. And we would assume that this last one is echo, 0 exponent, anything to the 0th power, 1. Quite unusual. But we had discovered that property doing a series of patterns of like 2 to the third, 2 to the second, 2 to the first, 2 to the 0. And we realized there was a pattern of repeated division. You can go check that out. So anyways, so that's some nice little flashback for you. Well, it turns out the same properties apply when you have rational exponents, right? So if I have little fractions in there, multiplying two things of the same base, I add the exponents, right? Power to a power, I multiply the exponents. I can distribute over multiplication. Negatives, right? Exponents get flopped downstairs. Everything's great. Still can do subtraction, still can do distribution. Now, you know what's weird is the properties of exponents, hopefully, I mean, it's easy to mix up, oh, when do I add, when do I multiply, I suppose. But assuming you got that down, those are going to be likely the things that are easier for us, and the challenge is going to be how to add fractions. Adding and subtracting fractions is going to be probably the harder part for you because we'll need to make sure we have a common denominator. All right, so example 1. Oh dear, they started us off real fresh, didn't they? Use the properties of rational exponents to simplify each expression. So multiplying two things of the same base, I would add the exponents. So a fourth plus a half. And that's where I'm like, wait a minute, I can't add those exponents. They have different bases. What is the common denominator between 4 and 2? Well, that's 4. And I could get that by multiplying this by 2 over 2. All right, tell you what, I'll write it out. So that's 7 to the 1/4 plus 2/4. Right? And so multiplying this was the same as multiplying by 1. I didn't change the value of a half. I just changed the way it looked. And 1/4 plus 2/4 is 3/4. And so 7 to the 3/4 power. All done. All right, let's do this. So here I'm going to distribute and multiply these because I can distribute an exponent over multiplication. And so that'd be 6 to the 1/2 times 2. And 4, this is being multiplied in between, to the 1/3 times 2. And multiplying fractions is not as difficult. If you want, you can put this 2 over a 1, and you literally just multiply the tops and the bottoms, Although in this case, you could do 1 times 2 is 2, and 2 times 1 is 2, and then divide, but I'm going to be even cleverer and just cancel those out. So I'm going to have 6 to the 1st power, which I guess we don't even have to write that one, times 4 to the 1 times 2 is 2, and 3 times 1 is 3, 4 to the 2/3. And I believe I'm going to leave these in rational exponent form. Although one could argue you could have written this as the 4th root of 7 to the 3rd. Or you could have even written this as the 4th root of the 3rd. Those are both equivalent to that, but I'll ignore that for the time being. Let's see, a couple different ways I could do this. I could deal with a negative exponent, move the whole thing downstairs before I distribute it. But tell you what, I'm gonna just distribute it first and then both downstairs. And I'm multiplying. All right, and for sake of time, 5 times negative a fifth is -1. 5 times negative a fifth is -1, and then I would move both of those downstairs. So that's 4 times 3. Who's left up top? A 1. And 4 times 3, I am able to multiply in this case and get 12. Notice here, I was not able to multiply 6 and 4 because this would have been equivalent to 6 times the cubed root of 4 squared. Okay, and so I can't multiply something that is not in a radical by something that is in a radical. That 4 was owned by that exponent. Couldn't multiply it in that way. Oh dear. Oh, you know what I did? Oh, that's funny. Mr. Wouty. Well. This part wasn't supposed to be here, nor this part. I gave you the book's first step on how to do that. But anyways, so 5 is the same as 5 to the 1st. I'm dividing two things of the same base, so I would subtract their exponents. So 1 minus a third. Oh dear, I can't leave that 1 that way. I'm going to get a common denominator. And so right now, between 1 and 3, the common denominator is 3. I'd multiply by 3 over 3 to get 5 to the 3/3 minus 1/3. It's tough writing fractions in exponents. They're so tiny. All right, and that is the same as 5 to the 2/3. And so that's, I assume, how they would rather we leave our answer now. But I do want to point out that's the same as the cubed root of 5 squared, or all squared, or I could actually square this 5 and make it 25. All sorts of stuff that we could do. All right, what's going on with this last one? Oh, that's weird. They like factored it out. You know what? We're not gonna. I'm gonna distribute and multiply is what I'm gonna do. Although actually that was interesting. They could divide the 46. I'll have to think about that. So let's see. So that's going to be 42 to the 2/3, because I'm multiplying those exponents, over 6 to the 2/3. And that is, okay. So yeah, because these are exactly the same, and a fractional exponent is the same as a cubed root. Actually, maybe if I write this in cubed root form, over 6 squared, although we'd have to remember some of our other properties, is the same as 42, cubed root of 42 squared. You can realize both of those are the same radical, and I also can't leave a radical in a denominator. And so that's why they were thinking of, like, pulling that out as shown. Also, one of the interesting things is, because both of these are in the same index radical, I could have reduced those. Actually, tell you what is 42? It's going to be massive. All right. 1764 over 36. Let's see. Does that divide evenly? That would be so wonderful, wouldn't it? Oh, I get the cubed root of 49. And so let's see. 49 is 7 squared. I can't simplify that anymore. This, by the way, could have been the same as 49 to the 1/3. Could have been the same as 7 is what they would have gotten here. 7 to the 2/3 power. So many different ways to write these. Crazy. Yeah, cubed root of 25. 6 times the cubed root of 16. 4 squared is 16. I could have actually cubed the, cubed the 7, right? What is that, 243 or something like that? So there's a lot of different ways to represent it. But the big idea is that all of your properties of exponents apply to these rational exponents, these fractional exponents, and so you can simplify in a bunch of different ways. All right, so here you would add the exponents. My foot's falling asleep here. What I get for sitting on my leg. So multiplying two things the same base, I would have had to add those. Here I would have subtracted exponents. Here I would have distributed, similar to that last problem we did. Here I would have distributed and simplified. I'm not going to take the time to go over these because it's a long unit and it's already a 12-minute video. Here we go. All right, properties of radicals. Now, if an nth root is the same as, right, if I have an nth root of something, that we already know is the same as a to the 1 over nth power. And since I can distribute an exponent over multiplication or division, and since radicals can be written in the same way as an exponent, it would make sense that you could distribute a radical over multiplication, and even nth roots. And technically, we've used that property in reverse when simplifying radicals earlier in this unit. And so you could multiply them together, you could break them apart, whichever way you want to use, right? You could go either way on these. And so fractions you can distribute over division, right? Good. So let's actually do this. Oh, Mr. Wouty, you did it again. You done doodled it. All right. Wow. So yeah, so I could multiply the insides here. What is 12 times 8? 12 times 18 is 216. And so I just write it under one large radical, and the cubed root of 216, I believe, is 6. No, what am I? Yeah, it's 6. Boom. Dunzo. All right, over here. Now, if it was helpful, there's actually a couple ways to think about this. I could write this as one large radical where I undistributed it, I guess. And then I could divide 80 by 5. That's kind of nice. 80 divided by 5, 16, right? And oh, fourth root of 16. No, you don't say. You don't say. That's 2. Wow, that's a crazy way to write 2. Now, I do want to point out, and I didn't earlier, you could actually skip this step. As long as both of those radicals match, same exact index, you can actually cancel this like a normal fraction. 5 goes into 5 once, and into that 16 times. It is possible to think about it that way. I just want to point that out. But there's a bunch of different ways that you can kind of rearrange to try to simplify these things. All right, and here we go. So since I'm making a unit out of multiple different kind of algebra textbooks, and I'm a crazy person, you've already seen some of this if you're in Mr. Waddy's class. We know how to simplify radicals. They have, right, if the number on the inside could be broken down, factored into the largest perfect cube in this case, because that's a cubed root, then you should do that. You can't have fractions inside of them. You can't have a radical in the denominator. And we had a few different strategies for dealing with that. And so, for, in this case, the cubed root of 135, what is the largest perfect cube that could go into 135? And so perfect cubes are like 1 and 2 cubed is 8, and 3 cubed is 27, and 4 cubed is 64. I feel like 27 might have a chance. Yeah, it does. It does. Hooray! So I could break this into the cubed root of 27 times the cubed root of 5 when I did 135 divided by 27. Cubed root of 27 is 3, and so 3 cubed roots of 5. So it's possible you've already seen us do some things like this before. They're tougher though. This chapter has tougher versions. So it's just like scaled up. Okay. Alright. Fifth root. Now, perfect fifths are 1, is 1 times itself, 5 times, and 2 to the 5th power is 32, etc. And so we're going to take that 32, and wouldn't it be nice if this was 32? Actually, there's a few different ways we can think about it. I'm going to have to get this radical out of the denominator. We've learned tricks as far as multiplying by, right, a radical over a radical to get it to be friendly. And there's a couple different ways of doing this. I want to multiply it by the thing that will give me a perfect fifth. All right, so 8 times what is 32? Well, that's going to be 8 times 4. And so the 5th root of 8 times the 5th root of 4 is going to give me something that can reduce in that denominator. That breaks down to 2. Now up top, I had to multiply it by that as well because this entire thing is equal to 1. And multiplying by 1 will not change the value of something, it just changes the way that it looks. And so this will be the 5th root of, oh dear, what was I doing? 7 times 4 is 28, and 5th root of 28, there's not a perfect fifth that goes into that, yeah, because I didn't go. And so this would be my final answer. Now another like little pro tip, if you have a hard time thinking of this, you could have actually written this in its prime factorization, but we've already done, oh dear, we've already done like adding fractions in this lesson, bringing back a callback, prime factorization. We don't have time to do a whole bunch of little things. So this would be the same as 2 cubed, and so since I wanted a perfect fifth, I would have to multiply it by 2 squared, because properties of exponents, 3 plus 2 would have given me 2 to the 5th, and a 5th root of 2 to the 5th, those would have canceled out, leaving me just the 2. All right, and so there is a way to like imagine these in prime factorization and be like, oh, so what would I have to multiply that by in order to get a 2 to the 5th? But we won't bother right now. Let's see, is any of these a good one? good ones right here. Tell you what, I'll take a gander at this. So here's a cubed root of 2. So I'd have to multiply by the cubed root of 4 because 8 is the next perfect cube that I could get that denominator to be. 104. Is that divisible by 8, I hope? It is. Okay, and so this would have been the cubed root of 8 times the cubed root of, what did I just get? 13. And so this would have been 2 cubed roots of 13. All right, you're twisting my arm. This video's so long. I gotta keep going. Last question, and you've actually seen something like this before in our previews. But the idea of multiplying by a conjugate, it's not quite the same, not quite the opposite. It's the conjugate, where just the middle number is different in this binomial type expression. And so in the case of 1/5 plus rad 3, I can't multiply by rad 3 over rad 3. It would get rid of this radical, but when I distribute, it would have gotten another radical in there. And so the trick that we had determined was, oh, if you have a two-termed expression, and this, by the way, only works if these are square roots, you multiply by the conjugate. All right, let's see if I can actually draw a 5 here. 5 minus rad 3, got to multiply the top by that as well. It's only fair because this is equal to 1. And so up top, I'd have 5 minus rad 3 over, and this is, man, this actually one lesson is pulling together so many old skills. It's a little bit scary. The reason conjugates are so great is because of this. If I multiply something by its conjugate, it's equal to the difference of squares pattern. And so I'm going to have the difference of squares pattern show up here. You could also FOIL this out, double distribute, and you'll end up getting eventually to the same outcome as me. But I'm going to say 5 here and rad 3 there. Continue down here, I guess. Up top is still the same. 5 squared is 25 minus rad 3 squared. That's just 3. And look at that. It ain't got no radicals in the debottominator. Over 22. And I can't simplify anything here. And even if I could, I'd have to just simplify it with a non-radical number in front of the 3. So here, just foreshadowing, I would have had to multiply by 6 plus rad 2. Over 6 plus rad 2. But this video is too long. I gotta get out of here. Guys, it's been great. Have a good day. Hope you enjoyed the lesson.